So, have you ever really wondered what a first-year engineering student gets up to in their very first electronics lab? What are those absolute fundamental things they have to master before they can even think about building the tech we use every day? Well, today, we're going to peek behind that classroom door. Using this official first-year workbook from Vimal Jyoti Engineering College, we're going to deconstruct the essential toolkit every single engineer starts with.
Okay, let's get right into it. Here's the roadmap for our journey, and it literally follows the exact path a student takes. We'll start with the welcome, go over the super important rules, get to know the components, learn their secret language, get our hands on the tools, and then finally put it all together to build our first working circuits.
So our guide for all this is course GXESL 106, the Basic Electrical and Electronics Engineering Workshop. And let me tell you, this isn't just some random collection of experiments. It's a really carefully structured foundation that's designed to build an engineer from the ground up. Right before a student even touches a single wire, the goals are made crystal clear. And you've got to notice, it's not just about the technical stuff. I mean, yeah, you absolutely need to know your components and instruments, but the course objectives, they start with safety and even include building teamwork skills. It's a whole approach to creating a well-rounded engineer, not just a technician. Okay, next up, before you get to play with all the cool toys, you have to understand the rules of the lab. And this isn't just about discipline, you know? In an electronics workshop, it's all about keeping everyone and all that expensive equipment completely safe. That number one rule, it really says it all. Safety is first, work is next. Everything, and I mean everything, flows from that. Keeping your bench tidy isn't just to make it look nice. It literally prevents short circuits. Setting your instruments to the right range isn't just a boring procedure, it stops you from blowing them up. This whole structured environment is completely non-negotiable. And how do they measure success? Well, this is where you get a real peek into the engineering mindset. See, getting the right result is only one piece of the puzzle. To get that excellent mark, you have to be prepared before the lab even starts, you have to follow the exact procedure, and, crucially, you have to understand the theory well enough to answer any question thrown at you. It's all about the process, not just the final answer. All right, we've covered the rules. Now for the really fun part, let's meet the cast of characters that make every single electronic device you own actually work. These are the absolute fundamental building blocks. So every component falls into one of two big families, passive or active. And you can think of it like this. Passive components, like resistors and capacitors, they can only manage or store energy that's already in the circuit. They're kind of like the pipes and dams in a water system. But active components, like diodes and transistors, they can actually control the flow of electricity or even amplify it. They're the pumps and the smart gates. First up is the humble resistor. It's probably the most common component in all of electronics. And its job is super simple, but absolutely essential. It resists the flow of current. It's basically the electrical version of a speed bump, and you use it to control how much electricity goes where. So how in the world do you figure out a resistor's value? They're way too small to print numbers on, so engineers use this universal color code. The first couple of bands give you the digits, the next one is the multiplier, which tells you how many zeros to add, and that last band tells you the tolerance, or just how precise that value is. It's a really, really clever system. Next up, we have the capacitor. You can think of it as a tiny, super fast recharging battery. It stores up electrical energy and then can release it in a quick burst. It also has this really neat trick. It blocks steady direct current, but it lets alternating current pass right through, which makes it absolutely essential for filtering signals. And just like resistors, capacitors have their own shorthand language. So a number like 104 on a tiny little capacitor doesn't mean 104. It means 10 followed by 4 zeros, and the value is given in picofarads. It's just another one of those compact codes you have to learn to speak the language of components. And of course, the list just keeps going. The workbook introduces students to diodes, which act like one-way gates for current, transistors, which are the fundamental building blocks of all modern electronics, acting as tiny little switches or amplifiers, and integrated circuits, which cram millions of these components onto a single chip. So, now we can identify all the individual parts. But how do you show how they're all connected together? For that, you have to learn the universal language of electronics, the schematic diagram. And this right here perfectly illustrates that language. That little zigzag line always means resistor. Those two parallel lines always mean capacitor. It doesn't matter if you're in Mumbai or Miami, an engineer can look at a schematic full of these symbols and know exactly how to build that circuit. It's a true global standard.
And for every single component that's represented by those symbols, there is an official instruction manual called a datasheet. It's put out by the manufacturer, and it tells an engineer everything they could possibly need to know. Its maximum voltage, its operating temperature, its precise dimensions. Every single technical detail is in there. Of course, just having the components and the diagrams isn't quite enough. You need to be able to power up your circuit, test if the parts are actually any good, and see what the electricity is doing. And for that, you need the tools of the trade.
This is pretty much the standard workbench for any electronics student. You've got your power supply to provide the juice, you have a function generator to create different kinds of signals, you have the digital multimeter, that's the real workhorse for measuring voltage, current, and resistance, and then you have the oscilloscope, which is like a magic window that lets you actually see electrical signals as waves on a screen. Let's walk through a practical example from the workbook. To test a diode, you set your multimeter to diode mode. You connect it one way, that's called forward bias, and you should see a small voltage drop, about 0.7 volts for a normal silicon diode. Then you reverse the connections. In reverse bias, it should block the current completely. If it passes both of those tests, you know the diode is working perfectly, just like a one-way valve. And now, this is where it all comes together. All the theory, the component IDs, the safety rules, the measurement tools, they all get combined for the final and, let's be honest, the most exciting step, building something that actually works. The student's canvas is the solderless breadboard. See, those rows of tiny holes are all connected underneath, so you can just plug in components and wires to create a circuit. It's totally temporary, which makes it perfect for learning, for testing out ideas, and for fixing mistakes without any fuss. And then comes one of the most satisfying first projects ever, blinking an LED with an Arduino microcontroller. This process really marries hardware and software. You build a very simple circuit on your breadboard, you connect it to the Arduino, and then you write a few simple lines of code to tell the Arduino exactly what to do. And this is the code that makes the magic happen. The setup function runs one time, and it just tells pin 13 to be an output. The loop function runs over and over forever, and it's incredibly simple. Turn the pin on, which lights up the LED, wait for 1,000 milliseconds, that's 1 second, turn the pin off, wait another second, and just repeat. That's it. You've just bridged the digital and the physical worlds. So, from safety rules to reading color codes, from schematic symbols to writing real code, that is the foundational toolkit of a first-year engineering student. It's a whole journey from pure theory to a blinking light that you brought to life yourself. It really is the starting point for everything that comes next, which leaves just one question. What would you build first?